Hello again. So, as promised, here we have an example on causality. So, example on causality, which will be the Lorentz Oscillator. So then I have to go through something really quick, which is quite important for the content we're going to develop here, and is the following. So let's say that we have a linear system. So what's really a linear system? So then just a simple definition about a linear system. So then a linear system is a system in which, let's say I have some excitation to my system x1 of t, and this excitation produces in turn a response, y1 of t. And then let's say I have another excitation here, so excitation x2 of t, which produces a response y2 of t. Okay, now a system is linear if, for instance, if I consider that how can I write this? So let's say that y of t is equal to the integral from minus infinity to plus infinity of the impulse response h of t minus tau times a chi of tau. And this is nothing but just some transformation on x of tau that I will define as t of x. See? Then a linear system, or a system represented by this transformation t, is linear if when y1 of t is equal to that transformation on x1 and y2 of t is equal to the same transformation on x2, because what the system does is that just transforms the excitation into something else somehow. So then this is mathematically in a way in which you can see the system. So just a transformation on the excitation that is applied to it. So then if that's the case, the system represented by transformation t is linear if y1 of t plus y2 of t is equal to the transformation of x1 plus x2. That means that if you apply x1 plus x2, you get y1 plus y2, being y1 and y2 the individual responses to x1 and x2 respectively. So then this is actually what a linear system is. So that means that the summation of the responses is nothing but the transformation on a summation on the excitations. And the linear system has the property that this is the summation on the transformation on individual excitations. Okay, this is more or less the definition of a linear system. This is called the reciprocity, the superposition principle. So superposition principle. And then we will see why this is important in our case. Okay, now for the time being, what we're going to discuss is the Lorentz Oscillator. And then the Lorentz Oscillator has susceptibility chi of omega equal to omega p squared divided by 4 pi times the summation on j of f sub j divided by omega j square minus omega square minus I omega gamma. Okay, this is how the things will look like. And then what we're going to do is that we're going to consider that this chi of omega is just the superposition of some chi's sub j of omega. Okay, and then we will treat chi sub j of omega individually. Chi sub j of omega will then be equal to omega sub p squared divided by 4 pi times some oscillator strength f sub j, which I believe I put upstairs. Yes, I did. Divided by omega j squared minus omega squared minus I omega gamma. And then the poles are obtained by making this quantity equal to 0. So that's what we're going to do with find p of omega equal to omega j squared minus omega squared minus I omega gamma equal to 0, which is nothing but the same thing as omega squared plus omega plus I omega gamma minus omega j squared equal to 0. Okay, and then using the formula to solve for variables in second order algebraic equations, then we get some mode with a plus sign with the minus sign, which is equal to minus I gamma divided by 2. This is plus minus 1 over 2 the square root of b squared, which is here I squared gamma squared, minus 4 AC, which is in turn is 4 omega j squared. And what we have here is just minus I gamma divided by 2 plus or minus 1/2 square root of 4 omega j squared minus gamma squared. If I put this 2 inside here, inside this square root, it goes as a 4. And this is minus I gamma divided by 2 plus minus the square root of omega j squared minus gamma divided by 2 squared. Okay, so then, and what we have here is that this omega j squared is the oscillation frequency of each mode in the Lorentz oscillator, and this gamma here is the rate at which the system dissipates energy. Okay, so this is what we have. So now that we have the poles of the system, let's just define the poles a little bit better. So then we just say omega plus and minus is equal to minus I gamma divided by 2 plus or minus some lambda j, where lambda j is defined as the square root of omega j squared minus gamma divided by 2 all square. Okay, so now what we have next is that we want to calculate the susceptibility chi sub j, but as a function of time, and then we write the following integral. So integral over some contour that we have to yet choose, the omega divided by 2 pi chi of omega e to the minus I omega t. This is for t greater than 0. Okay, and then what we're going to see is that the contour we're going to use, so let's recall what we saw in the last video. So in the video where we discussed causality, we discussed causality in the previous video. Then we define two possible contours. So if we have the poles here and the real axis, to guarantee causality, we said that just we analytically continue the poles, or we can do that whether for the upper complex plane or whether on the lower complex plane, and then we define two contours. One contour like this, one contour like this, and we said that this contour was C plus, this contour was C minus, where this thing here, since we're integrated from minus infinity to plus infinity, so then we defined that this semicircle here was of infinite radius. Okay, for both cases. And we defined that the contour C plus encloses no poles to guarantee causality. That's the restriction we impose for causality. So that this contour C plus encloses no poles, so then all the poles are enclosed by contour C minus, which is just a semicircle that lies on the lower complex plane. So then this is, of course, this is imaginary part of omega. This here is the real axis is the real part of omega, and then all poles are enclosed by C minus. Okay, and C minus has this orientation by definition, because we're going from minus infinity to plus infinity, and then we just come back. So then what we have to do in order to apply the right hand rule is to invert this the orientation of the contour. So then we take this orientation rather. So then that means that in purple, the direction that I just placed in purple corresponds to a contour minus C minus. Okay, that's the contour that it corresponds to. And that means that this integral that we have upstairs going to be calculated in principle over C minus because of the causality restriction, and this will be equal to minus the integral over minus C minus of the omega divided by 2 pi chi of omega e to the minus I omega t. This is how that will look like. Then yeah, let's do this. Let's write this again. So chi of t equal to the integral over that semicircle C minus d omega divided by 2 pi chi of omega e to the minus I omega t, and this is nothing but minus the integral over this semicircle, but in the counter direction, the omega divided by 2 pi chi, sorry, I'm talking about sub j here, of omega e to the minus I omega t. Okay, so and this is equal to minus 2 pi I times the summation of all the possible residues of the function here, this function. So then 1 over 2 pi chi sub j of omega e to the minus I omega t. Then 2 pi goes with 2 pi, and this is nothing but minus I summation over k of all the residues of chi sub j of omega e to the minus I omega t. Okay, so then we just have to recall here that the residue of some function f of z is equal to, let's say, the residue j, which is associated with the jth pole of f of z, is equal to the limit of z that goes to z sub j of z minus z sub j to the power of p times the function f of z. That's what the residue is equal to. So then and p is the multiplicity of the pole. So then in that sense, we can then write chi sub j of t equal to minus I summation of k residue sub k of chi j of omega e to the minus I omega t. Yeah. Then we replace what chi of omega is, and this is equal to minus I summation of k residue of omega sub p squared divided by 4 pi times fj divided by omega j squared minus omega squared minus I omega gamma times e to the minus I omega t. We just revert the sign here, and then we write minus I, or let's write plus I, the summation over all residues of this function here, which will in turn become omega p squared divided by 4 pi f sub j e to the minus I omega t divided by omega squared plus I omega gamma minus omega j squared. So we just pulled the minus sign from here and then plot it here. Okay, so then that's what we actually did. Now this we saw that this can be factorized by finding the poles as omega minus omega plus omega minus omega minus, and then we write I summation over all the residues omega p squared divided by 4 pi f sub j e to the minus I omega t omega minus omega plus omega minus omega minus, and then this will be equal to I, the first residue. What is the first residue here? So the first residue is the limit as omega tends to omega plus of omega minus omega plus omega p squared divided by 4 pi all times f sub j times e to the minus I omega t divided by omega minus omega plus times omega minus omega minus. This is plus the other residue, so then we just here, which is plus the limit of omega that goes to omega minus omega minus omega minus omega p squared divided by 4 pi fj e to the minus I omega t. See, so then here this is divided by omega minus omega plus omega minus omega minus. We close here, this one goes with this one. Let's see then what we're left with. So here we're left with omega minus downstairs. So then if we replace everything with omega plus here, then we in the first residue, so we get I, we get omega p squared divided by 4 pi f sub j, we get e to the minus I omega plus t divided by omega plus minus omega minus, and we get here plus omega sub p squared divided by 4 pi f sub j, we get e to the minus I omega minus t divided by omega minus omega plus. Okay, so what is it? What is it that we have here? let's factorize this thing here. So then we have equal to I omega p squared divided by 4 pi f sub j. We change sign here to be able to sum up the exponentials. So then we get e to the minus I omega plus t minus e to the minus I omega minus t omega plus minus omega minus. It looks good, so we will not take that long here. Omega p squared divided by 4 pi f sub j. Then here we replace everything, so this is e to the minus I. Here what we have here, we have minus gamma divided by 2 plus lambda j t minus e to the minus I minus gamma divided by 2 minus I gamma minus lambda j t. And then at the bottom what we have, so we have minus I gamma divided by 2, we have plus gamma j, then we have minus all minus gamma minus I gamma divided by 2 minus lambda j, close here and then close here. So then we're left with I omega p squared divided by 4 pi now let's take this factor. So the first one, it says minus I times minus I is I squared, so then we pick up here e to the minus gamma divided by 2t. This is positive here, so then we pick up a e to the minus I lambda jt. This is minus, we pick up the same factor, they're identical, so minus gamma t divided by 2. This is e to the what? To the plus, yes, now plus I lambda jt. Here then this goes with this, and then we are left with 2 lambda j. Then now let's see what we're going to do here. So then if we pull down this I here, it goes as minus I. Okay, and there's this minus sign. This minus sign reverts the nature of this sign, so then this becomes a plus and this becomes a minus here. So then let's write that down. Omega p squared divided by 4 pi f sub j e to the minus gamma t divided by 2. Here we have, let's say, divide this here by lambda j, and here we have e to the I lambda jt minus e to the minus I lambda jt divided by 2i. So now this looks like something. So what does it look like? So this looks like omega p squared divided by 4 pi fj e to the minus gamma t divided by 2 times sine of lambda j t divided by lambda j. And this is equal to, so what we have here is that then we have this susceptibility in time sub j, of course, which is equal to omega sub p squared divided by 4 pi, the oscillator strength, times sinc of lambda jt times e to the minus gamma t divided by 2. And because of the superposition principle, or the principle of linearity, so we can say that chi of t is equal to the summation over j of all chi's, which means that then chi of t is nothing but omega sub p squared divided by 4 pi. Yeah, let's include that here. So summation over j of f sub j sinc of lambda jt e to the minus gamma t divided by 2. This is the susceptibility as a function of time. So this came from a problem where we had all the poles in the lower complex plane. So then in principle this should be causal. This has no poles on the upper complex plane, but causality should be imposed. So then what we write is that chi of t is just equal to omega p squared divided by 4 pi times theta of t summation of j f sub j sinc of lambda jt e to the minus gamma t divided by 2. There is quite some interesting physics going on here. So then you just see that we have different oscillators there for every mode. So then we have a response function that goes as now this response function so we'll as we can see, we'll have to decay at the rate gamma 0.5 gamma. So then there is a let's say competition between gamma and lambda. See, so then this of course will give the specific physical phenomena that we were looking for. So if the system is really damp, so then what will happen? So if there will probably be an oscillation with a really short lifetime, and then it will decay off. So then this parameter is something that we have to play off, and usually in physics this parameter gamma comes from the environment, from the coupling to the environment. And it's really important to analyze how our system couples to the environment, at which rate does our system display energy off to the reservoirs, and this is some sort of questions that one has to ask in the type of problems. And so this is our first example for the causal. This is a causal Green's function. And we will see more about this in the next series of lectures. Thanks for